So now we've got to work out what happens with the scattering data, and this is not just the eigenvalues that remain the same, but a whole lot of other stuff. So we take u, which is a function of x and t, right? And we're going to compute omega n of x and t, which are the eigenfunctions. Okay, the eigenfunctions, the point spectra or something like that, with lambda n eigenvalue, so the omega n's are approximately some function Cn of t times e to the minus knx as x goes to infinity. Now remember, in our simple examples, they just were, this was just a constant, they had to decay like that, but you know, you can eventually you're going to run out and get kn, and kn is equal to lambda. Kn squared is equal to minus lambda n. So obviously kn is also conserved. And we're assuming here that the integral from minus infinity to infinity of wn squared dx is equal to 1, because we can always scale these. All right, and then we've also got these other scattering data, which is the plus the reflection coefficient. It's a function of k and t. Remember, this is the reflection coefficient exists for all k, so all positive k. There's no discrete spectrum here. You get a continuous spectrum. You get a solution for every k, and they're not bounded. And then it's t of k comma t. It's a bit confusing to have two t's here, bad notation. I call it a in the notes, okay? Rather than transmission, let's stick with that. So this is the transmitted wave. Often we write down t for it, but a here is the notation. Good idea. All right. So according to the, if it moves according, so we have the scattering data, which we call S lambda of 0, which is the, so we're assuming here t is equal to 0. Write that down. Well, this is, at t equals 0, this is given by, and it's the collection of k's, or the lambda n's, right, squared, cn of 0, and then this r of, okay, there's the sum of those, however many there is. There's always there's a finite number of these. There may be possibly 0. Okay, there's only ever a finite number. So that's the initial scattering data, and then at some time later, the scattering of our data evolves according to the following. Kn becomes Kn, they don't change. Cn of t becomes Cn0 e to the 4 Kn cubed t, and then r of k comma t becomes r of k comma 0 e to the 8ik cubed t, and the transmitted coefficient is a of k comma t, just remains the same. All right, so that's kind of amazing. So this system, when the solution evolves, the eigenfunctions evolve according to this theory. So what we could do is we can take the u and calculate the scattering data, then see how it evolves, and then calculate the u back. It's actually a very complicated and nasty method to solve the equation, but it's a remarkable mathematical structure, and it repeats and it can be exploited in lots and lots of ways. We're just going to talk now quickly about how to recover the function u from the scattering data. So it turned out that this is not a problem that's been well studied, because physicists wanted to know how to recover that. Scattering data is literally scattering data. You know, you scatter electrons off something, and they wanted to recover what the potential was. So we can recover, we can find, and it's not a simple process from the scattering data. The way we do it is as follows. We set up this function f of xt cn of t squared e to the minus kn x plus Alright, so this isn't very different from the, this is sort of like a Fourier transform representation of this stuff here. This is literally the Fourier transform of R, isn't it? So it kind of makes sense where this might come from. And in the case of the soliton solutions, there's no reflection here. So we're going to assume we're not going to ever try and compute with something with this term here. We're going to assume we've got these reflectionless potentials, and we're going to get rid of that, and we're going to show that we can recover the solitary wave. It's quite a process to do that, because that f of k doesn't lead us to u. We then have to solve this integral equation. So what we've got this function f, and then we solve an integral equation for k. So we want to solve for the function k. There's an equation for k plus f of writing this out. It's quite an equation. Okay, so that's our equation to solve. So it's an integral equation because it's got this integral here, and it's got the function f appearing, this is an x here, in two places. And this integral is with respect to z. So it's not too nasty. It's a linear integral equation where we trying to find this function k that would satisfy that. And we'll talk about how to solve that equation in shortly. And finally, this doesn't quite lead us to u, but we get u of x comma t. Our solution is equal to 2 times the x derivative of k of x comma t. So if you imagine trying to solve this thing, you set up the f, you plug that into this equation, and then you solve this equation, and then you finally calculate u from here. It's going to be quite a process to do that, but we're going to go through some examples and try and calculate that.